So students, so here in transient response, we are going to see two kind of time period. One is tau one and another is tau two. As you can see in the graph, t rise. The rise in the time is nothing but the time we start from zero and reach out to the maximum value. That is called t rise. As you can see here, t rise is nothing but t 90% tau 90% minus tau 10%. That means from the 10th% value to the 90%, if you want to see the difference of this difference is nothing but the rise in time. The square pulse, when we are able to apply to LED, it gives rise to rise time and fall time due to the two kind of thing. One is the diffusion capacitance, another is the junction space charge capacitance. So based on these two parameters, our transient response is going to obtain. So to get this particular thing, we have to see the rise in time and we have to see the fall in time. So rise in time means from the 10th% to the 90th%, if you're getting the increase in the time, that is called it as rise in time, tau rise. Similarly, if you want to find fall in time, that should be from t 90%, it is decreasing to t 10%. So it is what t 10 minus t 90%. If you see the difference of the reverse of it, tau 10 minus tau 90, then it is called as fall in time. So rise in time and the fall in time we can obtain by using this transient response. So to avoid the above current peaking is achieved using peaking coil in parallel to LED. So we'll use one particular coil in LED design in order to avoid the current leakage, current peaking. Means it's reach out instead of reaching to the peak value. If you want to avoid that by using a what? By using a parallel coil to the LED. Clear? So this is the parallel coil we are using to the LED. If you use this one, what is going to happen? This peak will be reduced and the short repetitive bias for the fall time also get reduced. So in order to achieve this particular thing, we are using a current of 2I is going to be fed to that particular response. At t is equals to 0 seconds, current through the coil will be 0. Means its initial value when there is no current, because we are connecting one inductor, right? What is the use of inductor? It is used to remove the peaking current to the LED. Similarly, double current through LED, if you take a double 2I, is enhanced injections. It's going to increase the injections and recombination of rate, reducing the rise time. So when we are going to take it, it's going to reduce the rise time that will be obtained by using this relation. So when we see this injection current, recombination rate reducing the rise time. So current gradually distributed in your inductor in your diodes. Both the way the current is going to be gradually distributed. Clear? So at t is equals to t1. Suppose t is equals to this is we are reach out to t1. At that particular time, what is going to happen? I is equals to 0. That means the coil tries to flow current in the same direction like a half Li square. Because we know the power of inductor is what? Half Li square. If you see the capacitor, it is half Cv square. We should know the energy value for both the inductor and the capacitor. Clear? So we are using at t is equals to t1. Whatever the current we are passing through the coil, it is going to be given the same direction, that is half Li square. The negative current I through diode brings injection carriers to the equilibrium faster. That means whatever the current we are passing to the negative direction, if you keep on increasing that particular current, and diode bring that injection to the carrier to become equilibrium, means making the both the side equal in order to produce a faster equilibrium. So that's the reason it is going to reduce the fall time as well. Clear? So this is the rise time and the fall time that can be what actually that can be peaking value. Whatever the peak value we do have, if you want to reduce that by using the inductor that is parallel to the diode. Clear? So that's what we are using in this direction. Next is temperature dependence. What is the temperature dependence is all about? Temperature dependence is nothing but whatever diode we are having. If you are using a temperature on x-axis, if you want to find the optical output power in milliwatts, if you want to find both the values, that can be obtained in this format. So what is the current we are assuming for that? I is equals to 200 milliampere. At that particular value, if you want to try to find out the temperature dependence of that particular output power, that is we are getting in terms of milliwatt, that can be obtained in this format. So as you can see here, we are using SLDE, LED, SLED. What all those things we are going to see now. The temperature dependence depends upon light emitting diodes, that is going to be obtain the internal quantum efficiency of LED that decreases exponentially. We know, right? Whenever we take any kind of LEDs, it is always taking the internal quantum efficiency. Whatever the quantum efficiency we do have, if you want to find that value for it, that can be always decreased in terms of exponential factors. So with increasing the temperature, what we are adding in that, we are adding the temperature. So light emitting diodes always try to decreases that edge emitter ELED we have seen, right? The edge emitter LED has lower output power than the surface emitting LED SLED, right? So we have seen the previous diagram, right? SLED, ELED. What is this SLED? LED is nothing but this SLED, that is nothing but switching LED. This is edge, right? So we are going to see both the things into consideration. So that's the reason here mentioned edge emitter light emitting diode has lower output power than the surface emitter LED. The edge emitter LED are more temperature dependent. So who's we going to take that more temperature coefficients into consideration? That is taken care of by the edge emitter LED that are more temperature dependence when compared to the edge emitter LED. Clear? So that's how we are going to obtain its functionality as well. Clear? Next part, how we are going to give the external quantum efficiency. So the basic thing for the external quantum efficiency is nothing but the Fresnel reflection. We have two kind of reflection, Fresnel and Fraunhofer. So here we are considering the Fresnel reflection. In this, what is actually the main criteria for that? It is nothing but whenever we pass any light to two mediums, one is the air, another is a semiconductor, right? This is my two medium. I want to pass a light from one end. This is my edge end. I'm keep on passing a light. All the lights is equally distributed in all directions, right? Because LED will pass all the current in all the directions. Not current, sorry for that. It's all kind of emissions of photons. That is nothing but the light will be spread equally in all directions. That means the transmitted radiation will be going to occur in all the directions. So based upon that, we are going to find the total internal reflection. So how do we get a total internal reflection? We know the definitions, right? Critical ray, when we are going to get, when you had angle of reflection is 90 degree, that time we are going to get the critical ray. Clear? Total internal reflection is nothing but at certain angle beyond the critical angle, if we are passing a light, it keep on internally reflecting in that specimen. That is called it as total internal reflection. So if you see this diagram over here, when light rays strike the boundary between the two homogeneous mediums through different medium with having the different refractive indices, a portion of light reflect back and rest transmitted further through the direction. For in that particular direction, there is not an internal reflection. So if you see, this is nothing but there is no internal reflection, but at certain angle start getting reflected in the same direction. If the light is passed in the semiconductor, it is coming back in the semiconductor only. Then this is called as total internal reflection. So clear? This is the diagram for external quantum efficiency. How we are going to get the quantum efficiency value for our given specimen. That can be obtained by using these two particular parameters. One is for the air, another is for the semiconductor. So that we can obtain by using this two analysis part. So here also we can see we had a main optical generation layer is there, from where our optics is going to generate it, and where from there we are going to get the optical rays analysis. Based on that only it is going to produce the optical analysis for it. The meaning is that whenever we pass a light, it will strike the boundary, right? It is going to cut the boundary between the different mediums. It can be a same medium, it can be another medium. It can be going to obtain by using the mediums. If you see that put the mediums when the light is going to pass, from there only we can able to obtain its medium analysis. So based on that angles, we are able to find out their transmitted radiations. Okay. So the patterns of the radiations we obtain after finding the patterns. Next criteria is to find the analysis. That can be done by considering their strikes. So that means by using the optical generation layer, we can able to find back emission as well. Clear? So the absorption region and the back emission we can able to find out. Now let us see what is the actual meaning of external quantum efficiency. The ratio of number of photons that we are finally emitted to the number of carrier crossing the junctions. Based upon that particular ratio, if you want to find how much number of electrons we are passing, that is nothing but how much number of photons we are getting from emitted part to the carrier crossing junctions. If you find both the ratios, we can able to find their efficiency. That means it is not same as internal quantum efficiency, which as only emit in all direction. Whatever the light is there in internal, it is going to emit in all direction of semiconductors. That is air surface is useful for that. Out of light in first region, only the light striking the emitting surface at an angle less than the critical angle. The angle is less than critical angle. If you want to find their analysis in that particular direction, that also can be obtained by using this particular phenomena. Next is some of the lights which we are putting in the second region will be reflected back at semiconductors. In internal quantum efficiency, this is going to happen at that particular point. If you want to find the semiconductor's edge surface, that due to the Fresnel reflection, this is going to happen. So there is the absorption of light along the path till emitting surface. So whenever we pass a light toward the internal quantum efficiency, that is also going to occur that the light is going to emit on the surface as well. So the efficiency of external is always less than the efficiency of internal quantum. Clear? So that's the parameters we do have. So what are the things we have covered in that? We have covered the external quantum efficiency, internal quantum efficiency, and how we get the efficiency basically. So efficiency is what we are saying. It is a ratio of number of photons which we are finally emitted towards the specimen to the number of carrier crossing the junction of that photons. If you find both the ratios into the consideration, we can able to find out the quantum efficiency. Clear? So based on that, we are able to find their efficiency value. Next thing, LED power and the efficiency. So how do we get that LED power? So which is basically power means whatever the current we are getting, current we are passing, if you do the square of that current, we can able to find out their efficiency, because power is nothing but voltage into current, or voltage square by resistance, or current square into resistance. We know P is equals to IR, P is equals to V into I. If you want to convert V in terms of I can write as I square into R, or V square by R. So here I am saying the excess minority carrier we can obtain by using this formula. Delta N is equals to delta N naught e power minus T by tau. If you substitute this both the parameters, we can able to find out their analysis as well. So in order to find out the equilibrium established at a constant current flow into the junction, that can be obtained by using the total carrier generation rate. How do we get the total carrier generation rate? It is equals to externally supplied plus thermally generated rate. If you take both the parameters into consideration, we can able to find the total carrier generation rate. So what is the total carrier generation rate in the sense? Whatever the supply we are giving externally and how much we are going to generate the given light, right? The thermally generated rate. If you take both the things into consideration, that is called as total carrier generation. So we know that current density in amperes per square meter is given by J, right? Current density is J. The electrons, whatever is going to injected across PN junction per cubic meter per second, but that is given by J is equals to Q by D. So J by QD, that is nothing but the formula for finding the electrons in the injection across that per cube, meter cube per second. So what is Q actually? The charge of the electrons. If you take charge, if you take thickness of the recombination region, if you take both the things into consideration, we can able to find out their density. Even we can able to find out the electrons, how much the number of electrons we are injecting in the PN junction. So same thing, if you want to find, this is nothing but the relation, students. So you have to remember both the relations. First relation is rate equation for carrier recombination in LED. How do we get rate relation in that? So D is equals to delta N by delta T. So or dt we can write. So D, if you differentiate that, J by QD minus delta N by tau. That is nothing but the formula for finding the rate equation for carrier recombination. So they will give the J value, that is current density, they will give the Q value, that is charge, they give the D, thickness, both the values they will substitute and they try to find out the relation as well. At equilibrium, what we can write? We can write whatever the delta value we do have, that should be equals to this value. So tau is shift on right side, equate with 0, equal to 0, this term equal to 0. So this here it will become 0. So this will minus will become plus. So delta N we can write as J, if you cross multiply, J tau by QD. This is called steady state current density at a constant current into the junction. Based on that junction's current, we can able to find out the relation. Based on that particular form, we are finding the LED power and efficiency. What is the power is all about? Power is nothing but we can able to find how much amount of energy we are releasing whenever we are passing a light towards the light emitting diode, and how much is the efficiency value. Efficiency means how much is the output power. When we are giving 100% of input photons, whatever the output power we are able to get it. So that is also we can able to find out by using the LED power and its efficiency. Clear? So based on that two parameters, we can able to find out their efficiency. Even we can able to find out their total carriage generated rate. That is nothing but whatever the supply we are giving input plus how much is the output is generated. That is called thermally generated rate. Suppose you are giving input as 12 volts to the LED. So how much is the output we are getting? How much is the light is going to disperse? Because we know, right, LED will give all the light in all directions. It is not in a specific direction, not like a laser, right? It is a spontaneous emission, not a stimulated emissions. So that both the things you have to keep in your mind whenever we talk about the LED analysis. So next thing, LED power and efficiency, the same concept. So what is our total R is equals to whatever the power we are passing, the supply, external supply plus whatever the power we are getting generated from the given laser, given find of thermally equilibrium point. That is nothing but thermally generated photons. If you want to find, if you take both the things into consideration, we can able to find out the total amount of their resistance, right? Resistance of the given specimen plus resistance of whatever we are getting from the from the given power, from the input power plus whatever output we are generated. So total number of recombination per second, R is equals to I by Q. What is I stands for here? I is nothing but the current, Q is nothing but number of charge. What is I is here? It's a forward bias current into the device. That is all axis carrier recombine either radiatively or non-radiatively. If it's taking the radiation, means if it is getting radiated in that particular direction, that is called it as radiated part. If it is not taking into the consideration, then it is called it as non-radiated part. If you want to find total number of radiation pattern, for that if you want to take, that is nothing but R of radiative power plus R of non-radiative, means it's getting the radiation pattern plus not getting the radiation pattern. If you take both the things into consideration, we can able to find out the total number of radiations. Clear? So based on that radiation, we have substituted and we can able to find out there n eta of INT is equals to whatever the radiated power by total R. If you want to divide that, cross multiply. So RR is here, it will be shifted this side. So NI of by, what is this I by Q we can write from the previous formula, right? What we have written for the previous formula here, we wrote it, right? J by QD is nothing but the current, electrons. Similarly, if you want to find whatever is the number of R is equals to I by Q, I can write. So that's I by Q I have written in terms of R. So that R I have replaced here. I have cross multiplied. Then I can find photon generated per second. That is nothing but the total optical power generated in that given specimen. How we got HV? H mu is nothing but the Einstein energy, right? So P in INT is equals to eta of INT. HV I by Q is for the watt. If you want to find PINT, that is nothing but the power of that particular value. If you want to find, it is nothing but eta INT HCI by Q lambda. That is also we can write mu is equals to C by lambda, right? So mu value, frequency we are writing in terms of C by lambda. So we have substituted all the parameters and we can able to find out their input power. Clear? Next thing, how do we obtain the LED power and its efficiency? So to get the LED power and its efficiency, we should know the external power efficiency. That is external power efficiency. We can able to find out by substituting the output power. That is nothing but optical power emitted externally from the specimen. That is given by letter PE divided by electrical power provided on that. So P. So PE by P if you want to find, if you take the percentage towards that, if you multiply with 100, we can able to find out their efficiency as well. So that's how we obtain the optical power emitted by PE into the medium of low refractive index, that is given by N. If you want to find the refractive index value by using the formula, we can obtain PE is equals to P in, because the input power Fn square. What is F stands for over here? That is nothing but the frequency of it into 4nx square. What is F here? That is nothing but the transmission factor of semiconductor minus external interface. Due to the Fresnel in reflection, all power whatever we are passing, that not be going to transmit outside. It will be going to transmit inside itself. Because of that, all the kind of parameters we can able to find out their power. Clear? So this is the LED power and its efficiency we can obtain by using these all relations. So what else we have learned, students? We have seen their external power efficiency. We are obtaining its optical power emitted by external part, that is given by PE by electrical power provided. That is nothing but output is the optical power, input is nothing but the electrical power. If you take output by input, if you take the ratio of it, if you multiply with 100, we can able to write that particular function as their efficiency. So efficiency is nothing but output power by input power given into 100%. The optical power whatever we are going to get, it is into the medium of low refractive index that is given by n from the face of planar LED. So we are taking a normal LED and that is fabricated from the material of refractive index of nx. So one material, whatever we are using, the emitted part having the n refractive index, and the input, whatever we are using, we are fabricating by using another material, right? N suffix small x, right? If you take both the values into consideration, we can able to find out it's PE. PE is nothing but the optical power emitted, which is nothing but the external part, that is the externally. So P is equals to P in Fn square by 4 nx square. We can substitute this way and we can able to find out their LED power. So next thing is about the laser light amplification. How do we amplify it? By using the stimulated emission of radiation. So now next we are going to learn about the laser, right? Till now whatever we have learned till efficiency, we have learned about the LED. LED is nothing but light emitting diode. It is using a multi wavelength, nothing but the not only single wavelength, it is used to multiple wavelength, right? That we have obtained. So based on that we can obtain a light, right? So how do we write for the first absorption? It is what we are passing with the energy E1 and E2. If you had H mu 1 2 is nothing but the input 1, and H mu 1 2 we are getting from the output n. That we both we can consider. Next thing, we want to find the radiation of it. How do we get the population inversion? Because the laser is going to find by using the stimulation, emission and radiation, right? So in that particular thermal equilibrium, the density of electron is non-excited. Lower level E1 is much more than excited level E2. So E1 is nothing but lower level, E2 is nothing but the higher level. So both we are considering E1 and E2. We can able to substitute both the values, and most the photons will emit will be observed in this particular direction. So whenever we try to observe that, the stimulated emission always try to be negligible. That means we cannot able to see that stimulated emission in that particular region. Next thing, the stimulated emission will exceed absorption only if population of excited, whatever the excited state is greater than that the ground state. If you had an excited state, if you want to see with the help of ground state, if it is increasing with that, then we can call it as it is nothing but the population inversion. Inversion is nothing but whatever we are observing that particular photon in this particular direction, if it is increasing with the excited state, that always greater than the ground state, means whatever the photon is there at the excited state should be much more than the ground state. If we are getting that kind of thing, then we can say it is a population inversion. The inverted population is not an equilibrium condition, because if it's reverse of that will be not an equilibrium, right? Hence it required the pumping techniques. It required different pumping techniques in order to obtain that. In semiconductor laser, it is achieved by injecting electrons into material. That means at a specific material, whenever we try to increase the electrons, that can be obtained by using this phenomena. So that phenomena we are able to obtain by using the laser. It is achieved by injecting electrons into material at a device contact to fill lower energy state of the conduction band, because we do have a different band, right? At a specific band it is going to produce a specific value. So when we see the conduction band, it is going to produce that. In PN junction diode, the forward bias applied to the injection E into the conduction band of the P region or hole are injected into the valence band of N region. So that means one electron is taking from the conduction band, it is reaching out to the valence band. So the bands of the energy is most important whenever we consider the injection carrier and the injection band. So we do have an electron is jumping from the p type material, it is going to the n type material. Whenever we are able to find out that particular material, that can be obtained by using the both the bands. The both the bands we can able to obtain by using the injection carriers as well. Clear? So that is how it is going to obtain by using the laser analysis. As you can see in the graph, what we are seeing in that graph, students, we can able to see the Boltzmann distribution with the thermal equilibrium. If you see Boltzmann equilibrium, that means the energy we should see, it is exponential factor of minus e power minus e by kt by using the Boltzmann. So what we are going to see in that, we are going to see that it is having some E1, right? The lower energy, that is the ground state, and E2 is nothing but the excited state. One is become conduction band, another is become the valence band. Always it try to decrease exponentially in the Boltzmann distribution of thermal equilibrium. If you see the non-equilibrium distribution, that can also be obtained by using the population inversion. The population inversion also going to obtain by using the exponential factor e power minus e by kt, right? So that is also we are able to find by using the density of atoms of n. So that is how we can write the population inversion of laser. Laser is nothing but light amplification of stimulated emission and radiation. That is the full form for the laser, right? So we know the laser. What is the laser is all about? So light amplification by stimulated emission of radiation. That is the full form for laser kind of light, which is going to take the two states. One is the ground state, another is the excited state. That can be stimulated by considering this formula. Einstein energy is equals to h mu, right? 1 2 is nothing but from input end. We want to find the output, which should be always in the phase only. If you see that electrons always in the phase, we can able to obtain by using these two relations, by using the stimulated emission radiation. That's how we can able to obtain the result light emission amplification and the stimulated emission of radiation. So that is the nothing but the population inversion. Also we talk about, we are seeing the graph of by the Boltzmann distribution, thermal equilibrium and non-equilibrium distribution of population inversion. The both the parameters we can able to find out, right? So next thing we are going to see the lasing action. Lasing action means nothing but the process how the laser is going to get the intensity in the one direction, how the laser is going to obtain the light. So that is called as lasing action. That can be done by using the two processes. First is the stage 1. In stage 1 what will happen? The forward bias applied to active layer and confining layer forming the PN junction. We have two kind of layers. One is the active layer, another is the passive layer. So the active layer is nothing but from where the forward bias layer is going to applied a confining layer forming the PN junction. So whenever we do have p-type material and n-type material, we try to dope, that is nothing but pentavalent impurity and trivalent impurity, try to make a octet rule, right? We know the octet rule. One is the pentavalent impurity and is nothing but the trivalent impurity. When both the impurities getting added towards that, we can able to find whole electron pair created. So that is recombined after carrier lifetime to emit spontaneous emissions. That the forward bias is gradually increased, causing the more pair and more emissions. Based on that, we are able to find out the lasing. Next thing, some of these techniques, whatever the photons we do have, that are going to be reabsorbed. That means we always try to give the photons to the laser to get the reabsorption of it, to create a more pairs, and some will stimulate pairs to recombine before spontaneous carrier lifetime, emitting the stimulated emissions, and the stimulated emissions increases with increase in the current. So whenever we increase the current from the stimulated emission, it is going to obtain from there. The stimulated emission increases with current, and the current at which stimulated emission is completely take over by the spontaneous emission is called as threshold current. Clear? What is the threshold current? At a particular current, when we try to stimulate the emission, means when we try to find the emission parameters, when it is completely take over the spontaneous emission, whenever we try to find the spontaneous emission in the given lasing action, that can be given to obtain by using our laser. So that laser is going to obtain that all actions, and that's the point we say that the stage 1 is been obtained and we can able to find out the thermal current. As you can see here, we do have a laser diode which derive the current, right? This is what relative optical output power. This is the output power we are able to find when we see the laser and the optical power. When we try to see the relation of that, we can able to find by using di and dp. So di is nothing but the increase in the current, and the dp is nothing but the stimulated emissions. When we see the lasing find, the lasing is nothing but the spontaneous LED type emission. It's similar to the like LED in this direction, in this region. If you see the LED characteristics and the spontaneity characteristics, both are same. But this graph is for laser diode derived current. Means always we should have some driver, right? If you see, if you want to go for the bike or if you want to ride anything, one should be the driver and another should be the passenger, right? So the driver is the one who can derive the given component. Like if you want to see the car, if someone want to derive that, that means someone external one needs to be derived. That's the reason that car can be able to move in a forward direction or it can be in a backward direction. In the same scenario, if you see the laser, in the laser as well, we have to have some external part, that is nothing but the laser diode drive current. There should be an external current. If you had a Thevenin's ITH value, if you want to see the current, this is x-axis the current and y-axis what actually we are taking power. If you want to take a difference of the power from the point at which it start increasing, from that point to it reach to the maximum value, if you want to find difference of both d2 minus di2 minus di1, if you want to find the difference of both, we can able to find the di. Di is nothing but the difference of that. If you want to find the difference in the value of with respect to that, we can able to find the slope. That's how we can obtain the thermal condition. So clear? So this is about the today's session, students. The next session we are going to learn in detail about the sensing as well as how the threshold condition is going to obtain, and its analysis part also we are going to cover. Thank you so much.